All right, good morning, guys. So I'm just going to go through these notes. Hopefully you have completed the videos on light and electrons. It'll make this a lot easier and it'll make a lot more sense. So make sure you have done that. If you haven't, it's not going to be the worst thing in the world, but some of this will be a little confusing. Let's get right into it. So pull up the PowerPoint so you have it, and also you'll have to fill in your notes too. I didn't put the completed copy on mine because you have something to do. You have to fill these in. So it says, first part, what is light? It says light can be described as a ray, a wave, and a particle. So we have talked about this a lot, how there's a duality nature of light and electrons, right? Electrons can both be particles and waves. Same thing with light. So there's certain properties in which it acts like a particle, certain properties in which it acts like a wave. The ray aspect here, that's kind of like ancient history, right? So this first part's talking about how people way back when in ancient times tried to think of light and how they had arguments between them in terms of what it was. So some people, so it says there, Pythagoras proposed that vision came from light rays coming from a person's eye, hitting an object. So his idea would have been, we have an object, here's your eye, give you some eyelashes, don't want to get dust in there. So his idea was particles came out of your eye, hit the object, and that's what allowed you to see it. And then if those rays didn't hit the object, you could not see it like that. Epicurus believed that objects produce light. So his idea was the other way around. We had objects, we had an eyeball, eyelashes, and things went, so this way, they went that way. Here, they're going towards your eye. Obviously, that's not true. So none of that is true. However, this one was a little bit more right than that one. So that's what this first part's showing. We're not really going to discuss it too much, plus you already saw the videos. Just a couple things to, I guess, note when we talk about scattering here, right? Think about, think about a mirror, right? So here's a mirror. When they're talking about light rays striking a smooth surface, well, and this is also talking about a particle. So another way that it acts like a particle is if you have a flat surface and light strikes it at a certain angle. I don't know, let's say this is 50 degrees. All right, well, it's going to bounce off at that same angle, 50 degrees. All right, another thing too, when they're talking about hitting a rough surface and they scatter, right? Think about light rays when they hit water, right? Water's all sparkly, it all shines and stuff like that. Well, light rays come in, it all comes off at different angles. So then you got some coming in like that, right? And then bouncing off. So, and you might be like, well, that angle isn't the same, but that's because it's a rough surface, so it's not perfectly even like a mirror. But that's why you see water sparkling, is light is hitting the water at different angles, bouncing off and hitting your eye, right? Eyebrows. So, right, when it's coming in like this, it'll then bounce off of the jaggedness, and then it happens to be pointing towards your eye, so that's why you'll see it all sparkling and shiny. So that's all this first part is trying to say. Oh, when we talk about refraction, what's that? Let's say we have a cup of water. Showing off my drawing skills here. Let's say you have a straw in there. You should be able to see this. Or if you go spear hunting for fish, it's full of water. So let's say the straw goes in the water right there. You will see it refract slightly. Okay. Reason for this is light is traveling at a certain speed. So it's traveling very fast. We'll say it's traveling fast here through the air. Once it hits this denser medium known as water, right, it will move slower. So that's why it bends, or you see it refract, because it's not moving as fast through this denser medium. That's all that's trying to show there, this first part. Okay, so you don't really need to know like everything that it says there. This next part here was talking about light as a waves, James Maxwell. You do need to know some of this information. This, not so much. This just kind of sets you up for the rest of it. So, light as a wave, James Maxwell. James Maxwell was actually considered, or he's considered like on par with Einstein, okay, in terms of his thought, or his revolution in thought in terms of how to think of light, and then also electricity and magnetism. So some things that you are going to want to know. I'll just get out a sheet of paper. Is this information, which I will quickly summarize. There's not, like, you don't need to know all of this, so to say. There's just certain parts that I will definitely make sure you know, or definitely make sure to mention. I'll pull it up a little bit more. So we'll talk about here, light is an electromagnetic radiation. It's radiation made of electric and magnetic fields. These fields vibrate at right angles to each other. So I could try to draw, well, let me just draw our wave first. Oh man, perfect. Just kidding. All right, so that's your wave, or that's an example, a 2D drawing of a wave. So what they're talking about here, and I think you probably saw it in the video, light is little packets of energy and radiation, right? So this is supposed to be the up, this is supposed to be the down. Why don't I fill it in? All right, so this is going up and down, and then you also have a section that goes from left to right. I know I messed up a little bit there. That's fine. So this one goes like this. Just draw it in like that. Right, so you have part of the wave, which might be the electric part, propagating up and down in this section, and then you might have, or then you will have, the magnetic part propagating this way. All right, that's why it's called electromagnetic radiation. And this is kind of like one quanta of energy. This is a small packet, the smallest packet of energy. Okay, and then these are going left to right. Like that. Okay, so let's label some information here. So this entire thing, it's a wave. Okay. The wavelength is, it says the distance between two identical points on a wave. So I'm going to do, let's see if I could fit it here. That's right, wavelength. And if you notice, this part is kind of the exact same point as this part. This is different because this part of the wave is traveling down, where here it's traveling up. So this would be the point where this wave would be traveling up here and then there. So this would be one wavelength right there. The frequency would be the number of waves that pass through a point in 1 second. So the frequency would be number of waves that pass through this point in 1 second. So because our waves here are moving so fast, 1 second is the best time. In physics, when you're talking about frequency and circular motion, you can't have a different time, but you don't need to know that for now. So amplitude is going to be this. So how high your wavelength peaks go, and there's also your troughs. So how low your lows go. But for now, amplitude is all you need to know, which is going to talk about how much energy is going to be in this wavelength. It's going to be a little confusing than what you expect, but we'll talk about that when we get there in a second. And then a node would be a 0 point, a point of 0 amplitude. That would be points like this. And it's not an arrow. This would be a node 2. These would also be node. It's supposed to be a node right there. So all that is, when this is propagating, so when this part is up, and then once it goes down, if you notice, this part is always going to stay at the same level. It's not really going to move when these things move up and down. Same thing with here. Well, this point is eventually going to end up here, and this point's going to end up here. This point always kind of stays at that same spot. All right. So, pretty much explained all this without even opening the packet. So, we got to right here. Okay, you do need to know visible light has a wavelength between 400 nanometers and 700 nanometers. There's plenty of other, right here. There's plenty of other wavelengths of light. You know, the ones with the most energy are gamma radiation. So most energy equals gamma radiation. And then lowest energy would be radio. Waves. Right? We can only see light between wavelengths of 400 nanometers and 700 nanometers. Why? Well, we don't know exactly, but a good guess would be that's the only wavelength that penetrates light. And what you're going to see here is wavelengths that are shorter actually tend to be more energetic. So that's over here. Oh wait, no, that's over here. So the shorter wavelength is actually going to have more energy, right? And the radio waves with the larger wavelength are going to have less. Why is that? Well, we're going to look at the math of it and explain why. I think I'm here. Am I? Hold on. All right. So you do need to know this equation. You do need to know how to use it. So the speed of light is 2.998 times 10 to the 8th meters a second. Lambda, that's what this is called, is the wavelength in meters or nanometers. You're going to see that it does depend on if it's meters or meters. Most of it is going to be in nanometers. You have to convert into meters. That is because our speed of light is in meters also. So if this was in nanometers, then you could just use nanometers. But since we talked about speed of light in meters, unit for wavelength will also have to be meters. All right, so I kind of already did the problem here, but why don't I talk through it? So what you need to do for these, and when it talks about what is the frequency of light with a wavelength of 500 nanometers. Well, first let's convert into meters. So 550 nanometers. Well, for every 1 meter, there are 10 to the 9 power of 9 nanometers. So 10 to the power of 9, you could think of 1 times 10 to the power of 9 nanometers. 1 up here, so 550 divided by 1 times 10 to the 9th. That's what that's supposed to be. And you will get 5.5 times 10 to the negative 7 meters. All right. So for this, what is the frequency of light with a wavelength of 500 nanometers? Light is always going to travel at 2.998 times 10 to the 8th. If you want, you can just round that to 3. 3 times 10 to the 8th. Okay? Well, we know our wavelength is 5.5 times 10 to the negative 7 meters. We want to know our frequency, which kind of looks like velocity. Sometimes it is written as that. So the key here is light is always going to travel at this speed. Okay? So this can change and this can change, but this is always going to be the same. So solve for your frequency. Divide by 5.5 times 10 to the negative 7 meters divided by 5.5 times 10 to the negative 7 meters. And you were going to get our frequency. And one thing that's kind of cool is this is meters a second. Our meters are going to cancel, right? And we're just going to be left with seconds, which is what our unit for frequency is. Hertz. So that's going to be 5.5 times 10 to the 11th hertz. All right, or that's how many times the wave or the wavelength will pass through a single point in a second. So a whole lot. All right, next, for this equation, done by Max Planck, he was the guy who discovered one quanta, or that basically energy or things don't receive like a linear amount of energy. They receive packets of energy, right? And only the smallest amount of energy as it goes up. So energy, things increase in energy in a staircase. Planck's constant, that is the smallest amount of energy that can be in a point in space. And that is the smallest amount of energy that things can gain as they gain energy. Obviously, they can gain trillions and quadrillions of these at a time, or even more than that. But that's what that is. So the energy in a wave of light is equal to Planck's constant times its frequency, which, right, we just solved up there. So this is going to change, and this will change, but this is a constant. So this will always be 6.626 times 10 to the negative 34 joules. Just a unit of energy. Physics, you know what that is. So the question is, what is the energy of red light if its frequency is 4.567 times 10 to the 14th hertz? Well, so we just plug it in. So we know 6.626, our smallest amount of energy that can fit in a point in space, multiplied by how many times that the frequency, so how many times that wavelength is in a point in space and time. Multiply those together. We're going to get some big numbers here. And you're going to get 3.026 times 10 to the negative 19th joules. So that's how much energy that red light had. And yeah, it's very useful. People still use this today. Think about all the electronics and screens that we have, and they have to calibrate how much energy that needs to light up, and how much the screen needs to use for battery life and that kind of thing. So you need to know how to use these. We're going to do some more practice in another video. One thing you do really want to know is in our energy equation, so this one, energy and frequency are directly related. So the greater the frequency, the greater the energy, okay? And then for this one, wavelength and frequency are indirectly related, okay? So because we have a constant c, speed of light, when one of this goes up, this one has to go down. When one of this goes down, this one has to go up. So when frequency goes up, or when wavelength goes up, frequency goes down. And when frequency goes down, wavelength, or oh my God, when wavelength goes up, frequency goes down. When wavelength goes down, frequency goes up. All right. So we'll do a little more practice with that later.